Good evening, everybody. This is Finite Element Methods lecture series 4, and this is the continuation of the last 3 lectures. And this is includes the formulation of finite element equations. So that is the major topic. So under formulation of finite element equations, we can see many different formulations, methods, and their method of solutions. So my name is Samayat. I'm from Indian Institute of Technology, Kanpur, originally from Ethiopia, Defense University College of Engineering, located at Debre Zeit, Ethiopia. So just to start today's lecture, I will start from the micromechanical analysis of structure. So most of our discussions are concerned about the structures which we are using in most aspects. So the structural scale is the analysis method that we can categorize the structure from the lowest element to the lowest atoms or quantum level to the structural level that we can classify it. So the classification also based on either time scale base or length scale base. So when we call in length scale, we start from 1 angstrom to some hundreds of meters. And when we categorize them in time frame, it starts from some femtosecond to some seconds and minutes, hours, and so on. So most of the time, structural analysis take place within this frame of analysis. So when we come to analysis scale, the smallest analysis scale is maybe quantum level. That means less than the atomic level or quantum level. Then it goes to molecular level. Then far from to the higher, again micro scale. And then mesoscale and macro scale. Then after structure will come. So the macro scale includes the structures and in the case of composite, the laminate. So this is the simple category of or structural scale of analysis. So we can analyze them to 1 angstrom, 1 nanometer. These are in the quantum level actually. Sorry. Again, in the molecular level, we can see hundreds of nanometer of the scale. So these are very small particles. So that goes from 10 to the power of 100 nanometer. And then in the micro level, we can see micro scale analysis. For example, in the case of composite material, we can take this as the micro scale as the fiber or a matrix scale. So a single fiber having diameter of 6 to 10 micrometer, so that the scale is micro scale. So that is, again, when we can take the matrix material, homogeneous matrix material, they are considered as micro scale at the in its constituent level. And then further going up, we can see the mesoscale, which is either representative volume element scale, or it can be of the lamina scale. Lamina means a single lamina. When we use composite, we stack a single laminas and increase thickness by adding more and more lamina on it. Finally, we can get laminate. So the macro scale indicates the scale of structure or laminate itself. Okay, so this is the scale of analysis of the structure. So let's go directly to our today's lecture, that is finite element formulation. So there are several approaches of formulating finite element, which can be used to transform the physical formulations of the problem to its finite element discrete analogs. So the first one is the continuum domains or the geometries. Are decomposed into discrete connected regions, which are called finite elements. And that is the direct stiffness method and the Galerkin stiffness method. The global stiffness method is used. The second one is if the physical formulation of the problem is known as differential equations, then the most popular method which we are using in the finite element formulation is the Galerkin method. And the third one is if the physical problem can be formulated as a minimization of the functional, then the variational formulation of the finite element equations are used. So here, the three important methods of formulations of finite element equations are direct stiffness method, Galerkin method, and the variational formulation method. Formulation of finite element equations. The premise is very simple in this, that the continuum geometries are decomposed or discretized into subdomains and then connected to regions, which the regions which connecting are finite element, and an assembly of the element level equations is subsequently solved in order to establish the response of the complete domain to a particular set of boundary conditions. The finite element method is, as we know, we already discussed this thing in previous lectures. So it is a numerical technique for solving wide range of complex physical phenomena, particularly those exhibiting geometrical or material nonlinearity. Actually, the part of finite element which deals with the geometrical and the material nonlinearity is called nonlinear finite element. So, such as those that are often encountered in physical and engineering scenarios. So, the problems can be structural in nature. As you have seen the scale of analysis, our problem domain is of the structural nature. So it may be electrical or magnetic or acoustic type. FM problems can be any type of, or the combination of this thing. So it is used most frequently to tackle problems that are not readily amenable to analytical treatments. Okay, so the most important steps which we use in finite element formulation are, the first thing is the physical formulation. And the second one is governing equations or and usage of boundary condition, and then finite element equation. So these are the three important steps in the formulation of finite element equation. So the physical object will be identified, and then that will be converted into some differential equation form, or it can be eigenvalue problem type. So then after applying the boundaries and formulating the equations, then we'll go to the finite element equations, which can be solved using either analytically or using some mathematical tools. So among the type of problems which the physical domains which we use for this type are, the the structural domain in the case of solid mechanics. For example, assuming the axially loaded elastic bar. Okay, so when the bar is loaded axially, that is under the category of structural or solid mechanics problem type. So the governing differential equation for such type of problem is this type: d over dx AE. A is the cross-sectional area of the material. E is the Young's modulus. Du dx is the strain of the element. So this is strain plus the body force B, which is equal to 0. So this is governing differential equation for the axially loaded elastic bar. Again, another formulation type is for fluid mechanics. Okay, so in the case of fluid mechanics, we have this differential equation, which is d over dx A E 2 mu dx. So dp dx the plus q. So this is the flow in pi. So this is the governing differential equation for flow in pi. And the thermal conduction, that heat flow. The equation for heat flow are d over dx. Most of the equations are almost the same, only the variable difference which we are using. Here we have material elastic constant E. Here's heat conductivity constant K. Here du, the axial displacement, the axial deformation du over dx. Here dt over dx, that the temperature distribution along the length. So when the Q is there, heat flux, so which is equal to 0. So this is almost the same. And the diffusion equation, one-dimensional diffusion equation, also the same. Again, electrical conduction equation. Okay, so electrical conductivity sigma is there, cross-sectional area, and so on. So these governing differential equations plus applying the boundary conditions, we can finally get system of finite element equation, which the system of finite element equation is K, the matrix of K, that stiffness matrix, the matrix of nodal vector U, which is equal to the matrix of force vector. So this is the finite element equation. So this is a simple explanation on how we can formulate the finite element equation. There are several finite element methods. From a simple, let us see the three most common methods of formulation. The first one is the direct approach, which in this case, this is the simple method for solving discrete problems in 1D and 2D problems. And the second one is the weighted residual method, which uses the governing differential equation. That is called the Galerkin approach. And the third one is the variational approach, which uses the calculus of variations and the minimization of potential energy. That is, we can consider this as some relativities method. So let's see the direct stiffness method first. We can see these three one by one in today's lecture, and further we can see them in many other lectures. So the direct stiffness method is considered as a good starting point for understanding finite element formulation. We consider first possible element, one elastic spring. Actually, most bar elements or structural bar elements are considered as an elastic material. So we can model them as an elastic with stiffness K. So let's consider the 1D elastic spring, which can accommodate only tensile and compressive forces. That means this is the axially loaded member. For the spring, we can see the spring system. This is the axially loaded bar having which is defined in terms of area A, length L, and the material Young's modulus E, and loaded with force F. So this is 1D bar element. So we can convert this as an spring material with spring constant K1. Okay. So to model this thing, the following conditions must be fulfilled. The first one is the condition of compatibility, which means connected ends or nodes of the adjacent springs have the same displacement. So this conditions is called compatibility condition. Again, the condition of static equilibrium. The resultant forces at each nodes is zero. The summation of resultant force, the force is acting at nodes is equal to zero. That means static equilibrium equation condition. And the third one is constitutive relation, that it must obey the Hooke's law of material, that the material is loaded under elastic regions. We are not going to include the non-elastic or non-linear portion of the loaded condition. So in the linear region. Okay, so that describes how the material responds to the applied load. So let's just see. The constitutive relation can be obtained from the governing differential equation for the elastic bar loaded axially along its length. So from the first, actually this one is not K, but we can take it B. So let it be K, no problem. But for our convenience representation, this case should be P, that the body force. Okay, so d over du, actually we can take this equation, So this is d over du, AE du dx. This is d over dx. It is my fault. So plus k, which is equal to 0. Then this AE du over dx is an strain, that is strain. We substitute strain here. And stress is equals to Young's modulus of material times the strain. So instead of these two constants, we substitute sigma, which is stress. And then force is equals to stress times area. Since stress is equal to force over area, so that this A sigma is equals to F. So dF du plus K is equal to 0. Then equating this, we can get dF is equals to K du. So this is, actually it is K dx. Anyway, this is the equation. So the spring equations relates the nodal displacements to the applied force through the spring element stiffness. From here, on the on E, we can see that equation number 6, which is a scalar version of equation. So derivation of from inspection, we can see that there are 2 degrees of freedom in this model, UI and UJ. These are the 2 degrees of freedom for a single member, for the axially loaded member. And the 2 ends are taken as the nodes, and the structure itself is taken as a spring with element E. So KE is our particular element. So Fi at force applied at the I node, and Fj is the force applied at the J node. So applying static equilibrium equation, just at each node, for example, in this node, we have k of an element, this element, times ui minus k of uj. Means it is k times ui, that relative displacement. Ui minus uj is the relative displacement at this node. And uj minus ui is the relative displacement at this node. So that we can use this equation. So k times ui minus uj, which is equal to force at I node, and k times uj minus ui, which is equal to force at node j. Okay, so in matrix form, these two equations, equation number 1 and equation number 2. So we can substitute the two equations in matrix form like this. Okay, so this is the matrix form. In short representation, this is the governing differential equation. This is the finite element equations for a discrete element, or for this single axially loaded bar. So let's take for two bars which are connected at node 2. Okay, so node 2 is there. Node 1, node 2, this is one element. From node 2 to node 3, there is another second element. So for two elements, we have 3 nodes. So the number of nodes are always in this kind of linear. We can say the total number of nodes are total number of elements plus 1. So the force applied at node 1, force applied at node 2, force applied at node 3. Okay, so the nodal vector u1 at node 1, u2 at node 2, u3 at node 3. Then we can apply the static equilibrium equation for each of them. For example, for this one, for the first one, we have this equation with this portion of the equation. And for the second, this portion of the equation, I can show it with some pen. Screen pointer, key pin. Okay. This plus this is for the first part of the equation, and for the second part of the equation, this plus this, which is easily represented with matrix representation. This is the matrix representation. Finally, this is the governing differential equation for not governing differential equation, but it is a finite element equation. Okay, this is the finite element equation. So note that share the K1 and the K2 at K22 because of the compatibility. So at this point, there must be a compatibility condition satisfied. At node 2, the displacement compatibility condition must be satisfied. Okay. Assembling the global stiffness matrix from the element stiffness. So this is K1 and this is K2. We separately formulate for this one this equation, and for this portion this equation. So both of them, we represent them as in matrix form like this. This is matrix form representation for element 1 and for element 2. Then we assemble these two equations. Okay. So due to the presence of compatibility condition, this K1 plus K2 of the node 2 will come in this point. Okay, so K1 minus K1 minus K1, K1 plus K2 minus K2 minus K2, K2, which is times U1, U2, U3, which is equal to F1, F2, F3. These are the nodal forces, these are the nodal vectors, and these are the stiffness matrix. So finally, this is the final equation. Okay. So let's see some complex systems consisting more than 2 springs. For example, in this case, we have 5 springs. Okay. For 5 springs, how we can model it? This is node 1, this is node 2. Again, there is another node here, node 3, node 4, and node 5. Actually, these are not nodes. In this case, it is simply linked here, linked, and linked. So we cannot consider it as node. So we have 5 nodes, node 1, node 2, node 3, node 4, and node 5. So that means the total degree of freedom for this system is 5. That the number of nodes indicate the number of degree of freedom. So what the meaning of number of degree of freedom or degree of freedom? That is the total number of independent coordinates to be solved. Okay. So let's see how we can solve for this. Okay, here this is now if it is we have 5 nodes, our matrix size is 5 by 5. For that reason, we can establish some matrix of 1, 2, node 1, node 2, 3, 4, 5, and 1, 2, 3, 4, 5. So this 5 by 5 matrix, and the nodal degree of freedoms are here: U1, U2, U3, U4, U5, and the nodal force F1, F2, F3, F4, F5. So this is the form that we must obtain at the end. Before going to solve this 5 degree of freedom thing or 5 spring system, from observation, simpler system, as we have seen in the case of 2 spring above, the following rules are required. The terms in location II, that II means in the same node, in the same position, in the same point. So II of the sum of direct stiffness of all the elements meeting at node I. Okay. The term in location Ij, that means I is one of the nodes, J is another node. That means the 2 nodes of an element, as we have seen here. I means this is I, this is J. I means maybe I like this, only in the same node. JJ means only in the same node. But IJ means the 2 nodes. So IJ consists of the sum of indirect stiffness relating to node I and J of all the elements, joining node I to J, are the negative force reaction terms minus Kij. Add 0 for node combination that do not interact. So these are some of the rules required. Anyways, so when we substitute the values of the five spring, for the first spring we have K1, K1, minus K1, sorry, K1 minus K1 minus K1 plus K1 here. This implies the first spring system, the first spring here, this is spring, it is in the first column and the first row, the second column, second row. So the entries are like K1 minus K1. Okay, I can say these are K1 and minus K1, K1. So this is for this spring. Here K2 is there for the next portion. K2 is there and K4 is there. K4. So what it is? Look here, K2 minus K2 minus K2, K2. So these are the K2 components. K2 components. And K4 is connecting, K2 is connecting second node and fourth node. You can see here. K4 is connecting node 2 with node 4. So this is the 5 spring or 5 link system that consists 5 by 5 matrix, and the entry of each of the links are for the first link we have K1 minus K1 minus K1. K1 is for the first spring, and for the second spring we have K2 minus K2 minus K2 and K2. So these are the entry from the second link or from the second spring, and the third spring is in connection with the second spring, so that we have K3 minus K3 minus K3 minus K plus K3 here. And finally, K4 is which joins node 2 with node 4, so that we have entry on the first column, the second column, second row, and the fourth column, the fourth rows. So we can find K4 here, K4 here, again K minus K4 here, and plus K4 here. And the fifth and the last spring is having K5 minus K5 minus K5 plus K5. So this is the entries, the diagonal entries. Okay, so this is 5 by 5 matrix. And in short, we can represent it with a matrix representation of Ku, which is equals to F. So matrix implies the nodal forces. So the unknowns in the spring system present are the displacement UIG. UIG means in the initial notation, which is we can let show you some. Okay, let me use pen. So Ku is equals to F is the system of the equation. Then, in order to take out the K to F side, we must multiply K by K inverse. K inverse K U is equals to K inverse F. Now, this K inverse K is the identity matrix I. Okay, so I times U is equals to K inverse of F. So, in order to solve the unknowns, the K matrix must be invertible. And if it is the K matrix is not invertible, then the problem of singularity will come. So this the multiplying I with U gives us only U. That any matrix multiplied by the identity matrix gives us the matrix itself. So that is equals to K inverse F. Yeah. So this is the form. So recall also that in order for the matrix to have inverse, it is determinant must be non-zero. Means if it is the determinant of the matrix is zero, that implies it is singular. That we cannot get a unique solution for the matrix. For that reason, the matrix must be invertible. Now let's take the two spring system that connecting two links together, and this is the matrix which you obtain for two spring. The first increase, this entry implies for the first link, that is for element 1, and the second, this part is for the second link for element 2. This numbering represents element number, and this is node numbers. Okay. So, which is so in order to find the determinant, we must know the mathematical concept of finding determinant. Actually, by three matrix, we can easily find determinant from a simple mathematical aspect. But if the matrix size is higher, then finding determinant is difficult. Anyways, for this 3 by 3 matrix, we have such kind of representation, multiplying A with this entries, EFHI. EFHI multiplied by positive A minus GH matrix. That gives us, and the determinant of the square bracket inside of this square bracket implies EI minus FH. That means A times EI minus FH. A times EI minus FH here, minus B times the determinant of the portion inside of the square bracket, AI minus FG, plus C times under the bracket DH minus EG. Okay, when we rearrange these terms, we can get this equation. Now, from our matrix of K, we can substitute in the place of A the first entry, that is K1. For E, it is K1 plus K2 term. K1 plus K2 term is E. And in place of I, that it is K. Okay, so we substitute this thing, and finally we get this matrix. So the determinant of this matrix, the K matrix, is equal to 0. This implies it is invertible. That means it is singular. So we cannot easily find the unique solution. From the system. So how we can apply boundary condition? Let's consider the node first, or node 1, as the point where our link is fixed. So if it is fixed on node 1, then node 1 has no displacement, or it cannot move, so that U1 of the node 1, or the nodal unknown, so U1 given 0. So this is the boundary condition. So once node 1 is fixed, U1 is 0. So let's put 0 in the place of U1 here. U1 is equals to 0. Okay, so finally, multiplying, taking the second part here, and finding the determinant for 2 by 2 matrix, what we can get, this is the remaining matrix. So the determinant of this is not equal to 0. That means we can get a unique solution, or we have a unique solution. So finally, we find the unique solution. F1 is equals to U2 K1 minus K1. U2 is equals to 1 over K1 the whole times F2 plus F3. And U3 is equal to 1 over K1 times F2 plus 1 over K1 plus 1 over K2 F3. So this is the U of values. So most of the time we use a matrix elimination method to find solution in a simple way. That is known as the Gauss-Jordan elimination method. So how we can apply Gauss-Jordan elimination method? In order to get the K inverse, we must use the Gauss elimination technique. For that, let's take a simple example of three equations, 3 linear independent equations. Equation number 1, equation number 2, equation number 3. Equation number 1, x minus 3y plus z is equal to 4. Equation number 2, 2x minus 8y plus 8z is equal to 2 minus 2. And equation number 3, minus 6x plus 3y minus 15z is equal to 19. This is 3 equations. Okay, so in matrix form, these 3 equations are represented in matrix form as this. And this matrix form will convert to the augmented matrix form. This is the augmented matrix, augmented form of matrix. So this augmented form of matrix is should be eliminated. So how we can eliminate, how we can implement the Gauss-Jordan elimination technique? Let's start the row 3 to 0, multiply row 2. Next, eliminate x from row 3. For that, row 3 is equal to 6 row 1 plus row 3. So row 3 is eliminated here. So minus 15y minus 9z is equals to 31. That is, and then let's eliminate y from row 2. For that, row 2 is equal to row 2 over 2. So by that, minus y plus 3z is equal to 5. So that is row 2. Minus 1, 3, y plus 3z is equal to minus 5. And let's eliminate row 3. Row 3 is equal to row 3 over 3. That gives us minus 5y minus 3z, which is equal to minus 11. 5 minus 3 minus 5, which is equal to 11. And finally, row 3 should be eliminated by row 3 is equal to minus 5 times row 2 plus row 3, which gives us minus 18 z, which is equal to 36. And immediately from this equation, this equation gives us minus 18z is equals to 36, which implies z is equals to minus 2. So once we get the z value, we can make a back substitution to the remaining x and y to the second equation. That is minus 1 y plus 3z is equals to minus 5. So by substituting in the place of z this value, immediately we can get the value of y. And continuing to back substitution, all three values will be obtained. So this is the technique how we can calculate the matrix or finding the inverse of matrix. So the next one is the second approach which we are using for finite element formulation, or is the Galerkin method. Okay, the Galerkin method. So let's take 1D example for explanation for FEM formulation of using the Galerkin method. Suppose that we need to solve numerically the following differential equation. This is our differential equation, which is with the boundary condition of u of x equal to 0 is equal to 0, and a du dx at x equal to 2n, which is at the free limit, which is equal to applied load r. So r at this end, at this position, load is point load or concentrated load is applied, and at this point the boundaries or the it is a fixed boundary, so that ux is equal to 0. So two ends are known now, and there is a body force which is uniformly distributed over the entire length, which is b. So now the bar is discretized into two elements, element 1 and element 2. Okay, so having the same lengths, length L and L. Length L plus L gives us 2L. So the total length of bar is 2L. So this is the so now this U1 and the U2 are the implying the distribution of linear elements. So x1 and x2 implies the nodes. Consider finite element presented on the right of the figure. That's this figure. Okay. So from that we can calculate the nodal deflection or the approximation function as u of x. That u of x is equal to n1 plus u1 plus n1 u1 plus n2 u2 for the element. So then this can be represented in matrix form n the square bracket n times u, which is equal to n1 n2 times u1 u2. So this is the matrix form of representation for approximate function of the solution. So n1, the shape function n1 is given as 1 minus x minus 1 over x2 minus x1. And then the two is x minus x1 over x2 minus x1. So what we are thinking is for this, for any x in between of this thing, for example, this is point x. If we consider this point x, then what we are saying x1, x is this point. So n1 and n2 are used for interpolation functions of u using its nodal values. And the nodal values u1 and the u2 are unknowns, which should be determined from the discrete global equation system. So now, by substituting the value of u in the place of in the differential equation, the original differential equation is this one. So if we substitute the u value of this u of x, this equation, then we can get this equation. Okay, d square of a times d square of this. A is the material constant, capital A, E. A is the Young's modulus, A is the area. So this substitutes area and the Young's modulus of material. So plus B is equals to psi. This psi is the non-zero residual. That is because of the approximation. Okay, so this is the representation. So the Galerkin meter provides residual minimization. So this residual function, this equation will be minimized using integration by part. We have to minimize it. So multiplying terms of the above equation by n, this m transpose is multiplied in both sides. Okay. So and it is integrated within the range of x1 to x2. Okay. So this equation n transpose. Okay, n transpose, then a d square of dx square that is integrated in the length of x1 to x2 with dx plus this one also multiplied by n transpose, this n transpose, and then so finally we can get this equation. Okay, so b dx is equal to dx. So using integration by parts, finally what we can get is this equation. After two successive integration, finally we get this equation. So this equation consists of the stiffness matrix. In this equation, for example, this portion, the integral of x1 to x2 dx transpose a dx. This is the K matrix portion. K. Here there is U. Okay, Ku. And this is the F portion, the force. F. Okay. So it implies what? Ku minus F is equals to 0. So this is the form of equation. Yeah. So Ku is equals to F. This is the form. So K means this portion of the first equation, and the F part consists of all these parts. Okay. So K is called the stiffness matrix, and F is called load vector. So this is the representation. And in short, for one element, we can represent K. K is equals to AE over N. Simply AE over N. So here A represents AE. So AE over N, 1 minus 1 represents for the first link. And as you see, the links are the same, and the length of the links is also equal at N, and the cross-sectional area and the youngest modulus of material also considered the same. K1 and K2 are the same. So they are A over N, 1 minus 1, 1. And F1 is BL over 2, 1, 1. F2 BL over 2, 1, 1 plus the concentrated load applied at the in load of that. This is the load at the inlet. And it is 0 at fixed position, and it is R at the free inlet. So finally, combine these equations for K1 and K2, because K1 is equals to this matrix, K2 is equals to this matrix. Then the first part of this implies K1 part. Half of this 1 plus 1. 1 plus 1. And also, from here, 1 is there. So it is the whole this part is K matrix, Ku, which is equals to F. So this is the representation. Here we have for F1 and the 1. For F2, 1 and 1. So this plus this will this is compatibility condition. These things will sum up. Here also they are summed up. Here also summed up. Yeah. So finally, substituting some value, that's A value equals to 1. Let the length L be 1, and the applied load R is equals to 1. Finally, what you can get is for this particular case, this is the solution. The titular line shows the great solution, and the dotted lines represent the FEM solution. Okay, so this is the solution. Now the surface one is the variational formulation. So this is also one of the most important finite element equation formulation method. So we can use also the same differential equation, but with the same boundaries and the same range of. Okay, so the same question. So with E equals to EA, which follows the physical solid mechanics, it describes In this describes tension of the one-dimensional bar is cross-sectional area E and elastic modulus E and subjected to distributed load E and central load R, concentrated load at the free end of the axial bar R at the right end, which is given as this. So for that, we use potential energy function. So the potential energy functional phi is given as the integral over the length of n 1 over 2a du of x dx as a whole square dx minus the body part. This is the body force part, integral over the length bu of x dx minus r of u of x is equal to a. So this is the potential minimization technique of directional formulation. So the diagram has two nodes, and approximation of the function of x can be done in this form because this is already calculated, or we found it in the first portion. So u of x is equal to n u. So substituting this thing to the equation using representation of u with shape function, which is written with the potential energy for the second finite level. So this is the form. Okay. Here also we get the same form as the previous one. Okay. Actually, the weak form of representation of the function. This is the weak form. So this variational formulation needs minimization of the function. Okay, so how we can make use of the minimization? So delta pi, which is equal to d pi du1 plus d pi du2 plus d pi dun, which is equal to 0. So this is minimization of function. So it is easy to change the differentiation of pi in respect to ui gives the finite element equilibrium equation, which is quantified with the equation obtained by the Galactic matrix, which is almost this equation. Okay, so this is all about. And actually, we can take some example with this. I can show some. This is the form of equation, what we are thinking. So let's obtain the shape function for one-dimensional quadratic element is 3 nodes using the local coordinate system. So that local coordinate system is the best way of using or calculating finite element solution. It gives the interval of -1 to 1. The zeta for one-dimensional element, zeta is in the interval of -1 to 1. So it is very simple and best way of describing finite element calculation. So for example, for the previous link, 0 to node 1, node 2, node 3, and containing 2 elements, element 1 and element 2, we can specify node 1 with -1 and the node 3 with +1 and the middle node as a 0. So this is the local coordinate system representation of finite element solution. So with shape function, any field inside element is present with u of zeta, which is equal to summation of and IUI. For the I from 1 to N3. In this case, I implies the number of nodes. Okay. In this case, we have 3 nodes, so I is 1 to 3. Then, at nodes, the approximated U2. So here it is U2. Here it is U3. So U of 1 is equal to U3. So this is U3. So this is an important step of finding solution. Now, the length of 3 nodes, the shape function can be quadratic polynomial with 3 coefficients. The shape function N1 can be written as N1, which is equal to alpha 1 plus alpha 2 zeta plus alpha 3 zeta squared. So this is a quadratic function where alpha 1, alpha 2, and alpha 3 are some coefficients which are defined from the boundary conditions, which are non-boundaries in the so at N1 N1 of minus 1, this implies the U1 value. So here N of x, or N is N of x, so N1 of x is equal to minus 1 implies alpha 1 minus, because this is zeta, the zeta value at N1 is alpha 1 minus alpha 2 plus alpha 3, which is equal to 1. Again, N1 of 0 at the middle, so alpha 1 is equal to 0. And N1 of 1, that means at the third node, alpha 1 plus alpha 2 plus alpha 3 is equal to 0. So, considering the first node, we have this thing. That means the shape function at N1 is 1, and at the N1 is in the third node, it is 0. So finally, solving this equation, because this alpha 1 minus alpha 2 plus alpha 3 is equal to 1 is one equation. Alpha is equals to 0 already now, so alpha 1 is 0. We have left alpha 2 and alpha 3. Equating these 3 equations, immediately we can get alpha 1 is equal to 0, alpha 2 is equal to minus 1 over 2, and alpha 3 is equal to 1 over 2. This shape function N1 is equal to then 1 over minus 1 over 2 zeta, 1 minus zeta. This is the shape function in the local coordinate system. Okay, so similarly, it is we have to find the N2 and the N3. This shape function actually at every node, we can evaluate at every node for the quadratic shape function. So for N2 it is 1 minus zeta squared, and for N3 it is 1 over 2 zeta times 1 plus zeta. This is N1 and N2 and N3. The shape functions are every node, each of the nodes. Okay, so this is the method of finding the shape functions using local coordinate system. So this is cited some reports to the thank you for watching the videos, and please give your idea whatever we can improve or the method of presentation. If any kind of query, please tell us. We can actually, this is a free video lecture. It is only for the benefit of you. Whatsoever we need your encouragement. arrangements for further improvement. So thank you very much.